Imagine you're an engineer designing a bridge. You need to understand the forces, or stresses, inside the materials.
At any single point, a tiny cube of material might be getting pulled, pushed, and sheared all at once.
We describe these forces using two types of stress. Normal stress, which we'll call sigma, pulls the faces of the cube apart or pushes them together.
We can also have normal stress in the vertical direction, which we'll call sigma y.
The second type is shear stress, which we'll call tau. This is a sliding force, trying to deform the square into a rhombus. Now for the critical question, what if we don't look at the element head-on, but instead slice through it at an angle? Let's call it theta. On this new, rotated element, we have new stresses, a new normal stress, sigma x prime, and a new shear stress, tau x prime y prime. To find these new stresses, engineers use a set of transformation equations, and they look pretty intimidating. Remembering these is a pain, but hidden inside this dense algebra is a beautiful piece of geometry. Notice how cosine 2 theta and sine 2 theta show up. Let's see if we can uncover that circle. First, let's rearrange the normal stress equation. Now we have two equations. If we square both sides of each equation, and then add them together, something magical happens. The theta terms disappear completely. What we're left with is this. This might look familiar. It's the equation of a circle. The coordinates are our transformed stresses. The center is at sigma average, and the radius r is determined by the initial stresses. This beautiful result is called Mohr's circle. It's a graphical representation of how stress transforms. First, the axes. Horizontal is normal stress. Vertical is shear stress. Crucially, we plot positive shear stress downwards. Step 1. Find the center of the circle on the sigma axis at the average normal stress. Step 2. Plot point A, representing the original stress state. Step 3. Draw the circle with center C and radius to A. Every point on this circle represents stresses at some angle theta. To find stresses on a plane rotated by theta, we move around Mohr's circle by 2 theta. The maximum normal stress, or principal stress, is at the rightmost point. The minimum normal stress is at the leftmost point. The maximum shear stress occurs at the very top and bottom, while the minimum shear stress is 0. So, what began as a messy set of equations transforms into a simple, elegant circle. Mohr's circle gives us a powerful way to visualize stress and keep our structure safe.